Good afternoon, this is Schweitzer. We're going to pick up our smart notes on a second aspect of our chapter, which is 2-1b, which is now going to deal with the electrons. Okay, and with that being said, there we go. Sorry, grab a pen, grab a little bit of a smaller pen. Okay, what do we got here? So we mentioned how hard it is for protons and neutrons to change or come and go. With that being said, electrons, not the case. They can come and go relatively easily, and all of the actual reactivity that you are familiar with of atoms, any kind of combustions, all of our lives, our whole life itself is based on taking or giving of electrons. We are not nuclear in nature. So that being said, we have a couple of terms here. Ion is a charged particle. All right, charged particle. And all right, so cation. Okay, obviously not pronounced cation, it's cation. This is where you're a positively charged particle. All right, so that's just something where your protons are a greater amount than are your electrons, whatever that happens to be. An anion is a negative particle, and this is just something where your electrons are a greater amount than your protons. All right, so that's your pretty standard stuff here, right? So up here, how do I go about calculating charge? Now again, this particular formula of protons minus electrons equals charge is probably something that I have never done, okay, to be honest with you. I just look at it, so okay, we have 8 protons, so we got 9 electrons. Okay, what element is this? First of all, it's oxygen, and I just sort of they cancel out, and we did it with a net -1 because there's one more electron, and we list that upper hand corner -1. Okay, the most common ion of oxygen would be -2, which would be 8 protons and 10 electrons. And this would be oxygen with a -2 charge, and that actually has a name called oxide. So sometimes when you have a "ide" at the end, that's a symbol of a negative. Not always. It's a symbol of a negatively charged particle, with its most common charge being that charge. Okay, so next up here it says, well, how does a student actually, or how does an atom actually become charged? Okay, so let's look at this here. Potassium's the most common charge is +1. So sometimes I'll diagram this out by saying, okay, what do we have for potassium? Potassium has 19 protons, and it has here still 19 protons. How many electrons does it have here? Well, it's got 18 electrons. 18 electrons. Over here, it's got a +1, which means it's got one more proton than electrons. So it only has 17. 8. Do here. Let's back this up here a second. Sorry. 19 and 19. Not sure how I lost one there. 19 protons, electrons. All right, they're the same. And then here it's 18. Thank you very much. So now what happened here? Now remember, this chemical reaction is just a snapshot before and a snapshot after. And everything that is here before must be here afterwards. So where did the one electron go? This side has 19, this side should have 19. So I'm going to put that right here. Okay. So what is this process called? Whenever you have electrons on the product side, or your initial individuals losing electrons, all right, electrons, we call it oxidation. Okay, that's an old term with a new definition. Okay, so in this situation, we call it oxidation. Very good. Okay, lose electrons oxide, so Leo. So notice that to become positively charged, would you ever lose a proton? And not likely. Not in our life on Earth. Okay, not going to happen. All right, next. What about a non-metal? Okay, so this case again, fluorine has 9 protons, and because it's still fluorine, still has 9 protons. It's neutral here, so it's got 9 electrons. We got, in this case, we gained 1 here, up to 10 electrons. All right, so protons are the same, but now I have 1 more electron on this side. That means I have to have 1 more over here, and we call this reduction. Okay, so for this guy to gain electrons, reduction. So Leo, the lion, says GER, and that is really what some acronyms, because this names of oxidation and reduction really have no more meaning. Well, the meaning still works. The name this thing here, reduction, really is referring to reduction of oxygen, and that still works, which is why it's still here. The definition, it still runs, but really now, for the most part, we're looking at it in terms of electrons, not oxygen. Okay. All right. How does an atom acquire charge? All right. So this is a pretty big topic here. Why do atoms form specific charges in nature? Okay. So here's the general idea here. Is that oxygen atoms, for example, we want to get to a more stable state. So lower energy, okay, typically means, okay, more stable. You'll see a ball, for example, rolling down a hill. Okay, you're not going to see a ball rolling up a hill all by itself. I'm not saying a ball can't roll up a hill, but you need to put energy in. You need to add energy, and that would be getting more energy, higher energy, not lower, and less stable, not more stable. So in nature, things rolling downhill would be losing energy, and this is just kind of what it does. So when oxygen goes from oxygen to oxide, then it's kind of like the ball rolling down the hill. It just goes to a more stable spot, and it's not going to go to. Is it going to go from 2 -3? No, that's going to go. It would go back this way. So it's kind of like a hill with a loop on it, where a ball is rolling down, and it just everything rolls to that point as being the most stable point. So how does this work? Okay, for us, again, we don't have all the answers, but it seems like a full shell indicates increased stability. Okay, we sometimes call this the octet rule. That's probably the most common thing we call it, octet rule. Now again, the octet rule is a pretty it's not a real it's not the best rule, okay, because, well, we also have the duet rule. So that would be for the first row. So technically the octet rule works really, really, really good for the second row, and that, I mean, that the second row follows this thing like the Bible, okay? It is absolute, and in this sense, the duet rule follows that guy. The third row, all right, it will kind of follow the octet rule, but there's some exceptions, okay? Because that's all the atom sets up, okay? So either way, how does this work? Well, atoms are always trying to get a full shell. So we're either going to lose electrons to get a full shell, or we're going to gain electrons to get a full shell. Either way, the noble gases, or the inert gases, already have a full shell. I'm kind of mimicking this because this is the metals and this is the non-metals. And they're trying to get to this point here. So metals tend to lose electrons or oxidize, so metals oxidize or rust. Non-metals gain electrons or reduce to gain electrons, reduce, lose electrons, oxidize. So in this situation, you could say, for example, an oxygen atom has how many electrons? How many valence electrons? So how do you know the valence? Well, they're really just the number, the column. 1, 2, 3, 4, 5, 6, 7, and 8. So there's your 8 there. So oxygen has 6 valence electrons. 1, 2, 3, 4, 5. I'm going to do that guy. We'll see more about why that is later, but in this sense, it needs to gain us one right here, and it needs to gain one here in order to give it a full shell. So right now, the oxygen has 8 positives and 8 electrons. If I gain 2 of them, one here and one here, now it has 8 protons and 10 electrons for a charge of -2. This is a pretty big concept. You should understand why oxygen forms a -2 charge, and you should be able to explain what I just told you. Everybody in this same family is going to do the same thing. All right, let's try lithium. Lithium has 1 valence electron. So if I drew it like this, okay, with 1 valence electron, well, now it's an opportunity. It needs to fill a whole lot of electrons, or it could lose. This is just the outer electrons. So valence electrons, keep in mind, valence is just the outer electrons. All right, and a Bohr model of an atom is one that we'll be focusing on later in this chapter, but would show this a little bit nicer. All right, so a Bohr model might look something like this, where it shows energy levels. Okay, so we got the nucleus. We have 2 energy levels for the lithium atom, and it's got 2 electrons here and 1 here. So that electron here is just this electron right here. So we're going to lose that guy, and now we still have our 3 protons and 3 electrons. We lose the 1, and we go to lithium with now 3 protons, but not only 2 electrons. So now it's got a +1 charge. And of course, we would need to put that electron right here if we're going to write out a whole oxidation reaction for this. Okay. All right. So that being said, the charges are being lost and gained. It's sort of get a break right here where you separate the gainers from the losers. These guys are all metals. That's the value of metals. And they are going to be losers, metal. All right, and this is going to be gaining, non-metals. All right, these guys gain this way, and we lose this way. Everybody here can lose to get over here, and everyone here gains to get over here. There are multiple, because these atoms here are bigger, there are multiple variations with what means stable. Having a full shell isn't the only way to be stable. So for example, we have copper, which is +1, and we have copper, which is +2. So this type of variation here can happen, especially when the atom's bigger and in the middle of the periodic table like that. Multiple options. All right. With that being said, all right, got another periodic table in the next one here, so let's just grab that guy and fill in that one a little bit. Okay, so what do we want to get out of this? So we want to make sure we know that the number of valence electrons are here: 2, 3, 4, 5, 6, 7, 8. And we would spend a lot of time in this in regular chemistry, so we're kind of glossing over this. This is the gainers here. Okay, so this is going to be gaining 1 for a -1, -2, -3. This is the teeter-totter point here, where sometimes we could gain or lose or neither. This guy is gaining 1 for +1, +2, and +3. And you should be able to realize and explain why this happens. Why does aluminum gain form positive 3. Aluminum is located right here. All right. So aluminum forms positive 3 in nature, and that's it. Okay, why is that guy doing that? Well, aluminum has 3 valence electrons. In order to get to a more stable configuration, it loses these 3 electrons and leaving behind a ratio that's a positive 3. So it's got 13 protons, and therefore it's going to have only 10 electrons. And there you go. Okay, that's a positive 3 charge. An important little correlation you may or may not notice is that if you look at a family, aluminum, calcium, magnesium, and sodium. So we have sodium, which is +1. We have magnesium, which is +2. And we have aluminum, which is +3. These are the most common ions of this particular set of atoms. That's this one, and this one. You'll note all of these now have the same number of protons as does this guy right here, which is neon. Neon's got 10 electrons, right? And so does everything else here. So we have this term which is called all of these guys are what we call isoelectric. Okay? Which means they have the same number of electrons. Okay? And when you have the same number of electrons as a noble gas, then that's probably a good sign because they are very stable. All right. Let's try another one. Aluminum has 14 neutrons and is neutral. Okay, complete the following. All right, give this a try on your own. Okay, what's the mass number? Well, for aluminum, 13 protons plus 14 neutrons is 27 mass number. That's the mass of the whole thing. For aluminum to become an ion, all right, sorry for that delay. For aluminum to become an ion, it will have to do what? Well, it's a metal, so it's going to lose electrons. It's going to oxidize. Right the reaction to be. So it's going to be aluminum goes to aluminum +3. Now, this is pretty easy for kids to get, but the number of electrons also is very simple. It's 3. Which side it goes on sometimes can mess with people a bit. This is no charge, and we just want to make sure the two sides are the same. Now, it happens to be 0 here, so we're not always going to 0. What we'd want to do is go to be the same. That'd be a legitimate reaction. So +3 and a -3 would equal 0. Same on that side. But if I put it over here, +3 over here, now I got a -3 on this side and a positive on that side. That's the same. So that would not be correct. So some people will just pick a side, make sure it works. What's the mass number of most aluminum atoms, and how many neutrons are typically present? All right. So the most common, well, the average is 26.98. 26.98. So that means the most common version is 27, and that is 13 protons and 14 neutrons. That's my answer. All right, and looks like we are going to stop there. Thank you very much.